All right, good. So this is week 7. Make sure that you go to the Facebook and post your answers for quiz 10 if you haven't done so in the lecture. And also this week we do have the PA number 6 due, which is relatively easy as well. All right, so hope you guys all have fun working on the quizzes and the PAs. And the topic today is going to be a bit light. The first thing we do is just to summarize chapter 2. Even though that in chapter 2 there's still section 2.7 which talks about circuit programming. Now whatever is in the textbook is mainly the Python-based circuit programming. Now as you have went through PA 1 to 6 and there are 3 more coming up, by the end of PA 9 you'll be able to implement there's a question. Yeah, so I'm going to go to the questions later. So by the end of PA 9, you'll be implementing a very simple web server, but a secure web server. All right. So I know some of you are looking forward to it. I'm also. Good. So chapter 2 is going to be a summary of all that we've talked about in the past few weeks, and it's a good time to give you the summary as well, given that the exam is coming next week. Now to conclude, we have actually studied quite a number of these network applications. All right. We've learned that some of them are running in the client-server model, but some of them, the road is actually fuzzy, everyone seemingly equal of another. Application layer service requirement, the QoS requirement, remember? There are 4 of them: reliability, bandwidth, delay, and what? Security. Okay. Internet transport services model, there are 2 of them, TCP and UDP. TCP provides reliable service, UDP, no, only the best effort. The specific protocols we've learned, HTTP, SMTP, POP, and IMAP are for the emails. DNS, P2P, we've learned BitTorrent, and we learned a little bit about Skype. We spent quite a bit of time here. Video streaming. Yeah, there's Dash, the protocol, as well as the CDN. It's actually an entire scheme with the structure of these CDN nodes. And last, this is more in the PA assignments. All right, so what we have talked about here is very brief. Well, the previous slide is more like an inventory of what we have already covered. Now, what I would really like you guys to keep in mind are these. You've seen, right, a number of these application layer protocols. One of the characteristics is this: server, client, or peer-peer, what they're exchanging are just a bunch of these messages, right? And it's very typical. There's a request and then there's a reply. Okay? So the client side requests, the server side responds. And each of these messages might carry a specific format. So there's a control part, which we call the headers or comments or status. And there's a data part, which we simply call data. And sometimes we call that the payload. Right? And so we now compare the control and the data. So by message here, I actually meant data. So the control bits and the data bits, sometimes they're sent actually together in a packet, in a channel. That is we call the in-band communication. So HTTP there, having headers and followed by data. That is very typical in-band communication. But FTP, in that application, we see control messages go on one TCP connection, and the data, the file upload, file download, goes on the other. And that is your classic example of out-of-band communication. Okay. So if you're designing an application yourself, designing an application layer protocol yourself, depending on the function you want to implement, you want to provide, you have to design for yourself whether you want it in-band or out-of-band communication, these bits that you are passing around. Now, some of the services, because the demand is low, having one server is plenty. Okay, so for example, file server, many of the file servers is just one single server. All right, so it's okay to keep it centralized because it's easy to implement as well. But we do see certain services gets popular, demand rises incredibly high, then we have no choice but to decentralize the service, and in the end having a certain hierarchy such as DNS service. Now again, when you're designing your application layer protocol, you might want to think about how popular it's going to end up being, right? And maybe design in a mindset where, well, eventually you need to extend. Then you probably keep a knob here and there to make sure that it's easier to extend. Would you like it to be stateless or stateful? You've seen examples such as HTTP being stateless. Well, there's a certain advantage doing stateless protocols because it's very simple. But then for some services, you would like to track the user's previous visit and relay that to the current visit. Then it might be more useful to do stateful design. You see also that it's extensible. HTTP was designed being a stateless protocol in mind, but extended using cookies to make it somewhat balanced. Okay, so we could keep some states about users if users agree. And yeah, this we know, right? Based on the QoS of the services you are providing, you will have to decide whether you want to use TCP or UDP. Therefore, the message exchange is reliable versus non-reliable. Now, this is probably something that you need not to worry about, right? Complexity at the network edge. Now, this is a notion we brought up discussing DNS. Okay, so DNS is what? The name to IP lookup service. Now, this is a very fundamental function if you think about it. Given a host name, before the message can even go out, you need to find the IP address. You see, the IP address is actually a notion down in the network layer, not even in the transport layer. It's actually further down in the network layer. So from host name to IP address, so DNS, to some internet engineers, should be a function provided at the network layer. But the reason that we implement it high up at the application layer is that designers are actually projecting how much load there can be. And the current design of the DNS system being centralized, chances high that it's not going to be sufficient. And it might be extended extensively. So having such level of complexity at the network layer, which needs to be implemented in all the routers inside the core of the internet, that is probably not a good idea, because whenever you need to change DNS, you need to bring down all the routers. And therefore, we have the DNS at the edges because we want that complexity being at the edge so that we could evolve quicker. And so that was chapter 2. And by the way, the midterm is actually not far away, only 2 weeks from now. So, hey, having a review like this is actually not bad, isn't it? All right. So how do you like that? And let me correct that. The midterm is actually coming up in 1 week because the video was recorded last week. And the next topic is going to be the beginning of chapter 3. Let's go ahead and begin. You know what? Polly is just happy that we're starting chapter 3. The transport layer. We were at the application layer that's actually higher up. Transport layer, we're getting closer to the heart of the internet. So in the transport layer service, there are a number of important functionalities. Multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Now each of these are important, but multiplexing, demultiplexing, flow control, these two are super simple. They'll be done in like one slide or a couple slides. Now, what's going to take us quite amount of time is this. reliable data transfer. And then slightly less, congestion control. All right. And both of these functions are implemented in TCP. Reliable transport, congestion control. Now then you can imagine UDP being very simple, right? It's a connectionless transport layer service versus TCP being connection-oriented. So in UDP, you don't need to set up something ahead of time before we send data. But TCP, you need to have a setup process before we begin to send data packets. 3.1 is the overview section. So what I need to say here is this. The transport layer services is actually providing a logical communication channel between the two processes that are running on different end systems. All right. So there's a sender side of the process, a sender side of the transport layer protocol, and there's also the receiver side of the transport layer protocol. And the functions is often corresponding each other. Sender side would take messages from the application layer and break it into a number of these smaller segments. And these segments will be passed down further to the network layer. Receiver side is going to take segments from the network layer, reassemble them back to the original message, and that message gets passed up to the application layer. That's when, if this guy here sends an HTTP request, this guy over here receives the HTTP request. So the web server here can begin parsing the HTTP request and then find out what is the object being requested, right? So this is the very basic function of the transport layer protocols. Take messages from application, break it into segments, reassemble segments into message, and pass it back up to the application layer receiver. Now, that breaking of the segments, passing of the segments, and reassembling of the segments are implemented in two different flavors, TCP versus UDP. One is reliable, the other is not. Transport layer versus network layer services. So transport layer there works closely with the application layer. It works also closely with the network layer. But we have not yet talked about network layer functionalities much, so let me just break it to you. What is the main role of these network layer protocols? So what they do is to provide communication between hosts. So meaning enabling sending of messages, sending of packets, or sending of segments through the internet and reaching the other host, the destination, from source host to destination host. Okay, so that is the purpose of network layer protocols. Transport layer, however, is just to establish a logical communication between processes. All right? So between two hosts, there are often multiple processes running. So transport layer handles a pair of processes at a time. Okay. So a pair of processes, and network layer handles a pair of hosts. The granularity, okay, of the channel, the entities of the channel are very different. Okay. So transport layer here rely on underlying network layer service. So if there's a process needing to send certain segments to another process, hey, how does the sending process know which way to pass it down further? Because internet is huge and in the middle. That is the network layer protocol's job. So logical connection between the sending transport layer and the receiving transport layer, that is kind of abstract. That's why I keep saying that it's a logical communication, because the network layer is going to handle and find a clear path between the two of them. All right. Now, let me try to use an analogy to explain so that it's more clear the distinction between a transport layer service to a network layer service. So the example is this. Anne here has 12 kids in the house, and Bill has also 12 kids in the house. Yeah, both big families. And for some reason, Anne's kids and Bill's kids are good friends to each other, right? So houses there, Anne's house and Bill's house, consider them as hosts. And each kid's generating letters sending to each other will be the processes. So 12 processes generating messages independently, okay, and trying to send them to Bill's houses and therefore reaching Bill's kids. So each letter generated by each kid is an application message. N and Bill will then be the transport layer service. So N here is the sending side of the transport layer service, taking all the envelopes and then drop it into the mailbox. So it's mixing all the envelopes into the mailbox. Bill, on the other hand, will take all the letters out of the mailbox and distribute each envelope to the destination processes, to each of the kids, right? So Bill there is demultiplexing the envelopes from the mailbox, and N there is multiplexing, okay, the envelopes into the mailbox. Now, the mailman, okay, taking all these envelopes from N's box and then go all the way to Bill's mailbox is the network layer protocol. All right, so mailman is the real person there needing to find a way and driving all the way to send all these messages. And there are two services again. TCP here does reliable transfer, but it actually does more. Packets are going to arrive in order. Packets, as they get sent, they will also be controlled. So sometimes you can send faster, but sometimes slower. And usually it's when there's congestion, then you send slower. If there's not congestion, TCP sender side will be sending more aggressively. There's also flow control, connection setup. Flow control is such that we do not overwhelm the receiver side buffer. Okay. Connection setup is, if you heard, TCP is a connection-oriented services as well. In order to provide these functionality, reliable transfer, in-order delivery, congestion control, and flow control, well, the sender and the receiver side of a TCP connection needs to, communicate a little bit more before setting up a connection. So that takes some time. So there's a connection setup process as well. UDP, on the other hand, is the complete opposite. It's not reliable, it does not guarantee ordered delivery. So UDP is essentially nothing versus TCP does a lot. So essentially at the transport layer, you have the two extreme of the services. Okay. So it's on top of the network layer, which is called the IP protocol, and it's best ever, meaning do nothing. All right, so no field extension of IP. And so UDP there is very simplistic. Take messages from application, break them into segments, pass it out. Receiver there, grab the segments from network layer, and then try to reassemble them back to the original message and pass it up to the application layer. Now, if there's any segment lost in the middle, that message gets passed up to the receiver side of the application layer protocol. It's not going to make too much sense, all right? Oh, and TCP, UDP, one does reliable transfer congestion control, the other does nothing. None of them provide this delay guarantee, bandwidth guarantee, and none of them provide security guarantee. Okay, and you heard it earlier, the security is provided by this alternative service, but this alternative service is in fact implemented in the what? Application layer. All right, so that was the overview. Straightforward, isn't it? Yeah, and I'm just gonna come back to the questions at the end of today. So the next topic, demultiplexing and multiplexing. 3.6, multiplexing and demultiplexing. Well, if you still recall the N Bill example, N's kids sending to Bill kids example. N is the multiplexer and Bill there is the demultiplexer. Right. So if we focus on this example below, so this guy in the middle is a big server machine. There are multiple processes running. You see here, P1 is sending a message out. P2 is also sending a message out. Yeah, the transport layer at the server is doing this. multiplexing. So this host here, from P1 and P2's point of view, generating this message, okay, is the sender. Okay, so sender. So it handles data from multiple sockets or data from multiple processes. Add the transport layer header. So add a little bit more information on top of these packets. Okay. And so therefore later they can be used for the demuxing purpose. So when messages go out and reaching P3 and P4, and P3 P4 in return generates something back as it arrives back to the server at the transport layer. Yeah, transport layer of the server is going to be working as a multiplexer at the receiving side. And what it does is to look into the header, okay, in these packets and then decide whether it should be this socket, the message being forwarded to, or this other socket, the message being forwarded to, right? So very simplistic, but very important functionality. Here's a little bit more how demultiplexing works at the transport layer receiver. Okay, so when a host receives an IP datagram, oh, this is yet another new term. These packets at the network layer are actually called the datagrams. You heard earlier packets at the transport layer being called what? Segments. At the application layer being called what? Messages. Yeah. So IP packets or IP datagrams will arrive at the receiving end of the transport layer protocol. Each of these datagrams will carry source IP address and the destination IP address. Okay. Each datagram will also carry a segment. So this is the transport layer segment. And each segment has these, the source port number and the destination port number. So these two informations being added. So to correspond with the demultiplexing process at the sending side of the transport layer, there is a message coming from the application layer. A segment, so a number of segments will be generated by breaking the message up. Inside each of these segments, we add some header information that contains the source port number as well as the destination port number. Okay, so that segment will go out to the network layer. So at the receiving side, okay, if you grab datagram at the network layer, you see a segment like this, and on top of that, the network layer header, which shows the source and the destination address, yeah, the source and destination IP address. Okay, so the whole thing here is an IP datagram. Each datagram has source and destination IP address in the header. Okay, each datagram also carry a transport layer segment, which is down here. So the part of the datagram without the datagram header. Okay, and inside this segment, you see these are the headers, okay, being added at the transport layer, and the remaining part is the application layer messages. All right, so you see here, data being generated by the application layer as it goes down one layer after another, a small header being added. Yet another small header being added, yet another small header being added. So that is the process of a packet traveling the internet. So that animation, I hope that you still recall at the end of chapter 1, right? And the host use the IP address and the port numbers to direct the segments to the appropriate socket. Now back to the lecture. If you think about it a bit more, multiplexing and demultiplexing, which one is more trivial and which one is less? Yeah, multiplexing, just collect the letters and shuffle it into the mailbox, right? No brainer. But mailman will have to, Bill will have to look at the envelope and see who the envelope is addressed to. So demultiplexing there is less trivial. Similarly, on the internet, the transport layer services receiver also needs additional information, just like names on the envelope, to do demultiplexing. So the information the receiver side of the transport layer service relies on are these. Okay, the source, destination IP addresses, and the source and destination port number. Now, let me explain. The host that's receiving a packet, it's going to see this, the IP datagram at the network level. Okay, not quite yet at the transport layer. We are now at the network layer, the receiver's network layer. So what we're seeing there is a packet that we call the IP datagram. So let's call this the datagram. Okay. So now a datagram is composed of the header part and the payload, the data part. Okay, so a header here and data here. Inside the header, there are these fields, the source and the destination IP addresses. Okay, so these information are kept there. So it's a network layer information. And each datagram also carries a transport layer segment, which is this, the data part of the IP datagram. So this here is exactly what's depicted on the side here. It's a segment. Similar to datagram, a segment is also composed of two parts, the headers and the data part. Okay. So the segment's header contains source and the destination port number as well. Right? So source, destination IP together with source, destination port number, they are the information to allow the transport layer services, the receiver side, to do demultiplexing. Okay, I hope this is clear. And the first form of demultiplexing is called the connectionless demultiplexing. And this is also the kind of demultiplexing being carried out by a UDP connection. All right. So in this type of demultiplexing, we rely only on the destination IP address and destination port number to decide which socket to pass a packet towards. So it's only a two-element tuple. Right? So when a host receives an UDP segment, it checks the destination port number in the segment and then direct the segment to the socket carrying that port number. And that's pretty much it. Okay? Now, of course, the IP address is important because the host at the network layer would be able to decide, whether this particular host is the destination of this packet, therefore keeping the packet and pass it up to the transport layer. And the transport layer could handle this. Yeah, receiving a UDP segment, check the port number, and so on and so forth. All right. So datagrams with different source IP address and different source port numbers, as long as they come to the same IP address, same destination port number, they will be going through the same socket. Okay, so demultiplexing for UDP is slightly simpler. All we care about is the destination address and port number. So here's an example of connectionless demux. So port 9157 is where P3 is sitting on. So that's one of the clients. Port 5775 is process P4 that is sitting on. So that's another client. Server in the middle opened up a port number 642A, and P1 there is the server processing. It's waiting for requests to come in. So we see here a service request message being generated from P3 and intended for P1. You will see source port number being 9157 and the destination port number being the server's port number 642A. And the return messages, so replies from the server would then be carrying the source port number being the server's port number and destination port number being the the sender's port number, the original request sender's port number, 9157, the client's port number. So you see also a little bit that how P1 can generate the reply. The port numbers are essentially the reverse, okay, of the requests. Now, if there's another request coming from P4, what is going to be the source port number? Yep, 5775. And destination? Yeah, the server's port number. And it's probably not hard. Yeah, the returning messages back to P4, source being 642A, essentially the reverse, yeah, of these two port numbers. The slightly more complicated one is the connection-oriented demux. That is also the TCP's demultiplexer. So whether a packet or a segment should go to a particular socket depends on all four information. All right, so receiver uses all four values to direct the segment to the socket. Now, a server process running there on the host could be maintaining multiple sockets, okay, for each pair of communication per client. So, for example, a web server, yeah, the web processes there could have multiple sockets open for each of the connecting client. And if this is older form of HTTP the web server is running, it could be one socket per object request. Now let me use an example to illustrate and explain. So we have a scenario where we have three segments being sent from clients over here, A and C, to the server in the middle, B. So all three segments destined to B, and they're supposed to be demuxed into different sockets. Now, P4 sockets will be using a 4-tuple to decide. And what will be the 4-tuple? Well, source IP address, A, destination IP address, B, and what? Source port number and the destination port number. So these four values is going to be associated with this socket. So when there's a segment arriving at the transport layer, matching the 4-tuple, therefore going to the socket. Similarly, for each of the sockets here and there, the 4-tuples will be stored, and the transport layer looking at the packet header, when there's a match, pass it up to socket to the processes. So that's the idea behind connection-oriented demux. And the reason it's called a connection-oriented demux is because it's not only looking at the destination, it cares also who the sources is. So it's almost like there's a one connection between the source and destination already, okay, the socket. Now, this connection-oriented demux socket is a little bit weird. And this actually happens quite often these days when we're doing this threaded server. Okay, so in your PA4, you are implementing a server, all right. What happened there is that you are starting a listening socket, isn't it? Listening socket is a little bit special because no matter where the client is, whatever the source IP is, request coming in is going to be passed to that server socket, that listening socket, all right, even though the 4-tuple does not quite match, especially the source IP address and the port number. Okay. This type of connection-oriented demux, it is TCP, all right, but it only looks at the destination port number and the destination IP address. Therefore, the message is coming out this way, source being A, source port number 9157. This one here, source being C, port number again different. But then they will all be accepted by the listening socket here. Alright, so if you recall in PAs, at the server side, you're actually creating two sockets, recall. First is the listening socket, which takes all sorts of requests coming from different sources, different source port number. Okay. But the data socket there you're creating, that is per client process. All right, so there are actually two kinds of connection-oriented demultiplexer, or
connection-oriented sockets. Now, quiz number 11, because multiplexing and demultiplexing is actually an important topic, although it's very straightforward. Just so that I emphasize this functionality so that you guys do not ignore this particular one. So this is quiz 11. Okay, and let me borrow from the mail delivering system. All right. So what you're seeing on the left, the picture 8 is the what? The mailbox, where you throw the mails in if you want to deliver one. And B here is what? A mail person grabbing all the mails out and trying to decide who's the receiver. All right. So Q1 here asks you which device is the multiplexer, okay, in the real mail, okay, delivery service, and which one is the demultiplexer. All right. And Q2 here, in the regular mail delivery service, what is really on the envelope that allow the demultiplexer to demultiplex? Okay, so how do they decide what's on the envelope so that the mail person here can know exactly which process or which exact socket to throw the envelope into? So this is Q11. Okay, it's very straightforward. So as you follow the lecture, you can just type up your answer in the live chat, and we'll just move on, right? And here's topic 4. Sorry, I did not update the topic 4 quite correctly, so let me just bring it up real quick. Some minor glitches here. Just give me a second. So in the meantime, feel free to type up the answer for quiz 11. And here, here is topic 4. All right. So we're going to talk about the connectionless demultiplexing service, which is UDP next.
UDP stands for User Datagram Protocol. As we've discussed many times, UDP does pretty much nothing on top of the network layer basic service. So we could have segment lost, we could have segments arriving out of order. So no reliability, unreliable. Second characteristic of UDP is this: it's connectionless. Therefore, there's no handshaking, there's no connection setup phase, there's no connection setup delay. As soon as we have data to send, we just generate these UDP segments and push it out. Very low delay. While we have also very low reliability. Right. But hey, some applications would actually like low delay, and it probably doesn't care too much about reliability. Then these applications would be perfectly fine using UDP as a transport layer service. So some of the video streaming services, some of the gaming services that we talked about uses UDP. Skype's voice sometimes also uses UDP. DNS, getting the host to IP mapping, we need it as soon as possible. Therefore, UDP here. Now, if one of these DNS query or reply is lost, DNS server, the local DNS server is going to send another request real fast, so don't worry. And SNMP, okay, we have not yet talked about this protocol. It's called the Simple Network Management Protocol. Now, this protocol is talked about in the textbook, but it's in one of the later chapters. Most of the content there is to talk about building a database, defining the format, such that when we measure, for example, round-trip delay from one host to another host, we get to store these round-trip delay data. We get to store packet loss rate data. We get to store available bandwidth measurement data. All right, so SNMP there define these data structure for informations that measures the performance of the internet. SNMP also gets set up across all the machines around the world. If they are enabled, these machines will send these SNMP messages back to the SNMP database. And those messages are sent using UDP because after all, these informations are nice to have, but they are not really necessary there to ensure the internet continues to operate. It tries to help such that the internet can perform a little bit better. But without these messages, the internet usually works just fine. Right? So those messages are also in UDP. Last point here. Yeah, UDP does not do reliable transfer, but some applications might need reliable transfer services, but not 100% reliability is required. Then those might add the reliability at the level the application desires, okay, and does application-specific error recovery. So this is one of the reasons people use UDP. Not only because some applications doesn't care about having segment loss, some applications wishes the messages being really fast, and some applications want some level of reliability but not perfect reliability. There's some other use of UDP. Right? So some other advantages of UDP. There's no connection establishment as we know, low delay. It's very simple, there's no handshake, it's easier to implement. There's also a small header. So this is a UDP segment. Once again, there's a header part, there's also a data part. The header part, very small, just 230 bits, 64 bits altogether, and that is 8 bytes. Very small header. There's no congestion control, so you can actually blast into the internet as fast as possible. All right? So these are a few other advantages of people using UDP. Okay. So there are 4 fields in the header. The source and the destination port number, which we've already talked about. The 2 other fields we have not yet talked about is lengths. This is the size of the UDP segment entirely, including header and data. And the unit to count the length is byte. Last is the checksum. What's interesting about UDP is that, hey, if you send data over UDP, there's no guaranteeing of reliable transfer, but you do get this. You get to check whether there's any bit errors in the data part of the UDP packet. And this is the way it works. It's called the UDP checksum. This is how it works. At the center side, we take the segment out. Okay, so take the entire segment including the header and lay the bits 1 row at a time, and each row 16 bits. So it looks a little bit more like this. Yeah. A row of 16 bits, another row of 16 bits. Okay, so you lay them out and then do what? Summing, okay, of these 16-bit rows. So add them up, and to be precise, it's called the ones complement sum to be exact. Okay. And as a result, you get also a 16-bit output. That is called the UDP checksum. Right? So let's come back here in the example to explain how exactly it's done. So sum, binary add, 0 plus 1 writes 1 here, 1 plus 0 writes 1 here, 1 plus 1 writes 0 here and carry 1 over here. That's why even though these two are zeros, we still get 1 down here. Okay, just do the binary addition all the way to the end. Now there could be extra bits being introduced. No worry, what we do in the ones complement sum is to wrap this around and then add back to the number here. So that 1 being added here writes 0, carry 1 over, writes 0, carry 1 over, writes 1 here, and that's the end. All right. Now the last thing is just to do what? To the complement. All right, so complement is straightforward, flipping 0 to 1 and flipping 1 to 0. And so in the end, we ended up having the checksum, which is also 16 bits. And this is what's being placed in this part of the UDP segment. All right, so when that UDP segment arrives at the receiver side, receiver does the exact computation, take the segment out, and compute the checksum. That checksum after computation is compared to the checksum field in the packet header. Right? If there's no bit error at all, right, the two checksums should match, isn't it? So if this equals this, if yes, then there should not be error. But now be careful, there could be specific bit error patterns that the checksum might not detect. Okay, so maybe error, but chances is very low. Right. But otherwise, if the checksum do not match, so there's clearly some error. Okay, so application layer there, finding a UDP segment having mismatching checksum can at least discard the packet, discard the segment, knowing that there's already something wrong.
All right, so that was all the lectures today. Let's go over the questions we have today, shall we? So let's start from the beginning. Okay. Yeah, so I can see that some of you are a bit anxious about the midterm exam, which is coming up. And yeah, I understand. You guys are probably thinking, how do I prepare for the midterm exam? Let me show you this first. If you guys know that from the course website, there's a link called the exams. Inside the exam page, you'll be able to find all the old exams there are. So this is fall 2019's midterm exam. So if you click into it, you see the exam from last year. Okay. So if you just scroll down, yeah, and read the exams, some of them, the answers are straightforward, so there are simple solutions provided. But some of the questions might be a bit open, then there's no particular simple solution. You'll have to think it through and maybe discuss that with your classmates, teammates, or if you like, confirm with Polly whether what you are thinking about answering the question is acceptable. So by going through a couple of these old midterm exams, then you should have a bit more confidence about the exams coming up, what kind of questions you can be expecting. All right, so yeah, so that's to address the first question. Tomorrow, I'm also going to show a very simple, short, okay, it's a testing midterm exam in Google form. So you guys can also take a look there. And I'm going to open up the Google form link so you can give it a try, because doing it online versus doing it right there physically in the classroom could be somewhat different. Okay, so you need to get used to it. Also for the midterm exams, you guys need to go find somewhere that has good internet and stable internet connection. So I highly recommend that you come to the campus and sit somewhere you have very good internet access, because we are also going to start a Google Meet session so that you guys can all join in case you have questions you want to ask during the exam. And you know what? That's kind of important, because if you guys, some of you ask a question, if it's online right there, everybody hears about it, then you guys will all be informed of what the bug might be. Okay, so this is to ensure fairness. All right. Now the second question is Rocket asking about PA6, whether the sleep time is going to be at the end of the handle connection or in the middle of it. Yeah, for PA6, because we're doing a file upload server. The server there, once receiving the whole file, then the job is pretty much done. So the server there's sleep time at the end is more to simulate, because that machine there could be just a load balancer or the first tier of the server. the file could be actually stored back to a remote server where the disk space is much larger. So it could actually be a physical database in the back. So the sleep time is to allow the server there, the contacting server, to do further processing, right? Now, last question. Yeah, so how you asked the question whether the port number assignment is deterministic or is it random. Pollys experience suggests that it varies a little bit from operating system to operating system. I see more how macOS's Unix works. It's more incremental and somewhat random. So it leaves a few port numbers open, just in case there are processes ongoing also requesting for ports for sockets. All right. So it's random, but it's kind of incremental random. Okay. And yeah, quiz 11. Very simple, very straightforward. So many teams actually address the questions very well. And David here is actually referring to register mail, where you have sender's information being very clear, as well as the receiver information. Because in the register mail, it's kind of important to ensure end-to-end reliability. So you see why in TCP it's a connection-oriented DMUX. Versus UDP, reliable delivery not required, therefore it's only connectionless. So all that's important for regular mail is just the receiver's destination. Right. Yeah, okay, Kevin was asking something more. Why does checksum use one's complement sum instead of the regular sum? That is a very good question. It is actually because the one's complement sum is actually very easy to implement into hardware. Those who have taken logic design, digital circuit design, you'll see that one's complement sum is actually very easy to compose. I think just add gates and negate gates, just a very small number of them. It's actually easier to do than the addition, the regular addition, the regular binary addition. All right. So that is actually the reason. It's a bit odd, only because the hardware is slightly easier to implement. So because checksum it needs to be done for every packet, right? The number of packets arriving at the core router there could be a lot of them. So doing checksum is a process that needs to go really, really fast. So oftentimes we have hardware accelerators, and that is why we use the one's complement sum for the UDP. All right, good. So I see Team 7 also supplies solution to quiz 11. And that should be all for today. If you have any further questions, feel free to type up. I'm going to leave the session run for a little longer and close that in a couple minutes. Tomorrow, make sure that you ask your classmates to come sit in and try the test midterm exam out so you get a bit more confidence. So to join the test Google Meet session, so you get a bit of idea what kind of bandwidth requirement you might need. Okay, so that's all for today. So feel free to go, and I'm just gonna leave the session on for a few more minutes. All right. Oh yeah, there is. The description is already available. I can upload it if you can't wait to start it. The video, however, the companion videos, however, will take maybe just a couple more days. So let me put it up, the description. Okay, I think this is a good time to end the stream. I'll see you tomorrow.